Hello everyone, welcome back to Study with Sup. I am Safia Khalid and you're watching the MSRT IoT Lab series using Raspberry Pi 4B. This is the second experiment under this series and today we'll be implementing a 3-bit binary counter. The flow of this particular video is divided into 5 parts. We'll be starting with the resources required, followed by the circuit diagram, and then with the Python code. The fourth part is the live demonstration of the working and the various connections, and we'll end the video with a brief summary of the topics covered in this particular video. Let's now get started. First, the resources required. First and foremost, we need the microprocessor. In this case, we are using the Raspberry Pi 4B. And then, to indicate the binary count, we are using the LED output device. Whenever an LED is used, we will be using a current limiting resistor. Here the letter N indicates the number of bits of the binary counter. Since we're using a 3-bit binary counter, N will hence be 3. For this particular experiment, it is highly recommended to use the breadboard to easily connect the components. And for connecting the components, we will be using the jumper wires in addition to the breadboard. Now coming to the circuit diagram. This is a basic circuit diagram of the Raspberry Pi 4B. We know this is the electrical symbol of an LED. The positive and the negative are nothing but the anode and the cathode respectively. And we look at the actual LED component. The long leg of the LED is the positive or the anode, and the short leg is the cathode or the negative side. Since we're using a 3-bit binary counter implementation, we need 3 LEDs, and we've named them from L0 to L2, L0 representing the LSB and L2 representing the MSB. Each of the LED has its corresponding resistors. In this case, we're using the value of the resistor as 330 ohms. And each of the resistors are first connected to the corresponding GPIO pins. We'll be using 2, 4, 6 in this case. The other end of the resistor is connected to the anode or the positive of the LED, and the negative or the cathode of the LED is connected to ground. In this way, the basic GPIO pin connections with the LED and resistor is done. Apart from that, we need to connect the micro HDMI port of the Raspberry Pi to the monitor. The keyboard and mouse are connected using the USB ports, and we will be giving the power supply to the Raspberry Pi using the USB-C port. When we look at the 3-bit binary counter, it produces values from 0 to 7 in the case of up count, and values from 7 to 0 in the case of down count. Hence, any binary counter will produce the values in the power of 2 power n, where n is the number of bits. In our case, n is 3, so 2 power 3 is 8, and the values are from 0 to 7. Now, let us have a look at the Python code. The first 2 lines are the libraries required. In our case, we need the rpi.gpio library and the time library. It can be imported using the import command. And this particular library can be taken with the alias name as GPIO. Instead of this, you can use any other name, and you can also use a camel case or lowercase, it doesn't matter. But to make sure that the code is readable and it instantly gives the correct meaning of what we're intending to do, we will keep it as GPIO itself. The time library, it is required for all the time-related functions such as the delays, etc. The rpi.gpio library, it is required for the various functionalities of the GPIO pins of the Raspberry Pi, such as the set mode function, setup function, etc. The next part of the code, we are defining the GPIO pins. We're using 3 GPIO pins for 3 bits, and we'll be using the variable pin1, pin2, pin3 respectively. These numbers can be any number of your choice as per the pin diagram. I have selected 2, 4, 6. Next, we're going to be setting the mode of the GPIO using the gpio.setMode command. And in this case, we're using gpio.bcm. BCM stands for Broadcom mode. So the basic idea behind using the BCM pin numbering is that if I'm selecting pin number 2, it corresponds to the actual GPIO pin 2 of the Raspberry Pi. The next few lines are the setup, wherein the GPIO pin's direction is set as either input or output. Since LED is an output device, all the 3 pins are set to output using gpio.out. Next, we are using a count variable, which will indicate the up count or the down count. In this case, we're implementing up count, and this variable will help us keep a track by acting as a counter. Now we're using a try except block. Within the try block, we are having a forever loop implemented using while true statement. And first and foremost, we are having the logic as follows. Here, each of these values 001, 010, 100, it indicates the condition of the particular LED. 001 indicates the LED at the LSB position, 010 at the middle position, and 100 the LED corresponding to the MSP. And also another way of looking at the correctness of this is pin 1, pin 2, pin 3, and we are having the logic such that we are performing a bitwise AND operation between the count variable and the particular positioned LED. If this particular function turns out to be true, that particular LED will turn on, else it will remain off. If we consider the initial state wherein count is 0, in that case the bitwise operation of count and 001 remains 0, which is false, hence pin 1 will be false or will not turn on. Similarly, pin 2 and pin 3 will also remain false because of the bitwise AND operation resulting in false. If we take another example, which is 100, which represents the number 4, in that case, we have count value being 4 represented by binary 100. Since bitwise operation of 100 and 001 is 0, the LSB LED will remain off. The middle LED will also remain off because the bitwise operation of 100 and 010 will again be 000. Finally, when we come to 100 and the count value is also 4, both when performed bitwise AND, the MSB position LED will turn out to be true, and hence the pin 3 GPIO, which is connected to the LED L2, will turn on. Each of these value of the binary count, such as 0 to 7, it will stay true for a period of 2 seconds, after which we increment the counter by value of 1. So if initially the value was 0, after this particular position, the value becomes 2. This is nothing but the shorthand form of telling count is equal to count plus 1. Next, since now the value of count is 1, it will not enter the if loop because it's still less than 7. Once we keep performing the looping function and we reach the value of count is equal to 7, when we reach this position, the incrementing value of count will result in count equal to 8. In such a case, it will enter the if loop because now 8 greater than 7, and we will again make the value of count as 0. That is, we'll reset the count variable. Once that is done, at any point we can exit the code by using the keyboard interrupt. Keyboard interrupt is done using some control signals such as control plus C. When that is done, it not only exits out of the program, before that it will also clean up the states of the GPIO pin so that when we run a new program, it will not create any warnings or errors. Now, point to be noted is that there is a slight error in this part of the code because we have an if block, so the next statement should have a particular indentation and it should be given at least a tab space from this particular position. So before running the code, you need to correct it. The correct code is available in the description box. This was just to show a particular error in the if block. Now, this is the correct code with no errors. Whenever we use any kind of block, the try block, the while true block, or the if block, the statements which follow the colon, all of them should have a particular indentation which is certain spaces away from the start of the previous block. It can be either a single space distance or it can be a particular tab distance. Hence, two errors have been fixed. The indentation with respect to the while true block has been fixed, and also with respect to the if block has been fixed. Now, let us move on to having a look at the live demonstration of the experiment. Connections have been made as per the circuit diagram. We first have the gray wire which is connected to the ground terminal on the Raspberry Pi. The adjacent slots are internally shorted, hence all of them represent the ground voltage level itself. Now, actually we had to connect each of the cathode end of the LEDs to the ground pin on the Raspberry Pi. However, this would lead to extra connections. Instead, just by connecting the wires to the breadboard, it will represent the same voltage level. The other terminal, which is the anode of the LEDs, connected to the corresponding resistors. We have three LEDs, so three resistors ends are connected to the three anode of the LEDs. The other end of the resistor is now connected to the GPIO pins. We have used the GPIO pins 2, 4, and 6 in this case. The MSB is connected to 6, LSB to 2, and so on. Hence, these were the basic connections as per the circuit diagram. We can see that the LED of the LSB is continuously on. This is because internally it has a pull-up resistor, because of which it is continuously on. However, if we make use of any other GPIO pin, this would not be the case. And even when the program is not running, all the LEDs will be off. Hence, it's not recommended to use GPIO pin 2 unless it's for any operation related to I2C. In a later part of this video, we'll also see what are the changes if we use another GPIO pin, which is nothing but GPIO 17. Now, this is the Raspberry OS interface. I'm going to be using Genie's Programmer's Editor for our particular experiment. The up count using GPIO pin 2 for the LSB has been displayed. We're using a 3-bit binary counter displaying values from 0 to 7. The logic, everything is the same as the code shown. I've compiled it and compilation finished successfully message has been shown. Now next I'll be running the file. We can see that initial state, all the three LEDs are off except the LSB LED. We can see the demonstration of the binary count going from 0 to 7. Yeah. Continuing the loop again, 0. We have 1. Now we have 2, 3, 4, 5. If I click directly on cancel of the terminal, we see that whatever was the previous state of the LED, that remains as is. This any other previous state is not erased, and the clean up statement which is given under the keyboard interrupt doesn't get activated. However, in order to make sure that all the GPIO pins are reset to the default states, we need to make use of some kind of control signal. In our case, we will be using the control signal Control C, and when we use Control C and exit out of the program, we see that despite, for example, if the previous case was 4 and the MSB was on, that LED will not remain on when I exit the program. Only the GPIO pin 2 LED is on because of the internal pull-up resistor which exists. Next, we'll see how the LEDs react if the GPIO pin of the LSB LED is changed from 2 to 17. So I'm just changing the bio from 2 to 70. And I also have the corresponding code ready, wherein I've changed the value of the pin 1 to 70. On running this particular code, we see that the basic functionality is happening as is. However, when I think of exiting the code using Control C, we see that all the three LEDs are now off. The first LSB LED is not on by default because no longer any pull-up resistor is involved. This particular experiment can be extended and we can perform the functioning of a 3-bit down counter. All we need to do is make few changes to the count statements, such as the counter variable needs to be set to 7 in the case of 3-bit counter, and correspondingly we'll be having to do down count. So instead of increment option, we'll be giving minus decrement by one value. And also the if block will be changed. Instead of telling count greater than 7, we will be changing it to count less than 0. Whenever count becomes less than 0, we'll be resetting the count variable to 7. In that way, we can implement the down counter. Now when we run it, we see that it started from 7, 6, 5, 4, 3, 2, 1, and 0. The down count from 7 to 0 was implemented and the loop continued. And when I give Control C, we could exit out of the program without any issue. This particular program was executed by using GPIO 17 instead of GPIO 2. Hence, when I exited the program, none of the LEDs were turned on because it did not involve any pull-up resistors in the process. Now, that was the demonstration. Coming to the brief summary of the entire experiment. On the left is the circuit diagram with the 3 GPIO pins connected to the 3 resistors and the LEDs. The entire functioning of the circuit is represented in the form of a truth table. 3 LEDs L0 to L2, MSP position, MSP position. And for a 3-bit binary counter, the values in the up count is from 0, 0, 0 to 1, 1, 1. When it is 0, 0, 1, only the LSP LED is on, the other two are off. When it comes to 101, the first and the last, or the MSP and the LSP LEDs are on, whereas the middle LED is off. So every 2 seconds, these LEDs will remain on and off corresponding to the actual values of the binary representation. Whenever the binary representation of particular bit position is high, that particular LED will be high. That was the end of this particular experiment. Thank you for watching. If you haven't subscribed already, please do subscribe for more videos. Also like and share this video if you found it useful. These are the thumbnails of the other videos. Check them out if interested. Thank you.